Okay, we are going to spend 2 more days really looking kind of at the surface of polynomial functions because we are splitting 813 into day 1 and day 2. So today we're really only going to do the front of the note sheet that you printed off. So we are looking at 45 to 47, and then for the next lesson we will finish off 813. So it's reminding us in the beginning of the note sheet that in lesson 812 you found possible equations for graphs of polynomial functions based on the x-intercepts. Many of the sketches that we used did not include a scale on the y-axis, okay? And I kept saying kind of ignore how far up or how far down the peaks and valleys are going, because when we looked at Desmos, sometimes that came up to be like 500 or negative 500. So in this lesson, what we're going to do is figure out equations that represent all of the points on a graph. So we're going to really focus in on accuracy on the x and the y axis. So we are on 45 to begin, and we are posed with the question or the task to find reasonable equations for each of the polynomial functions. Then the key idea of today's notes is, without using a graphing calculator, the question that's being asked is, how can we check the accuracy of our equations? And then we're going to evaluate, were the equations correct? If not, is there something that you can do to correct them? Okay, so just a little bit of review from last week. Let's do a graphical analysis on A. So we see that the end arrows are opposites and they're behaving like a normal cubic function where the first arrow is decreasing, okay, and the second arrow is increasing. Okay, so we know that that is going to be an odd degree function because it's opposite arrow direction. And then because these arrows match the parent function of the cubic, we are going to call that positive orientation because it behaves as normal, down then up. Okay, now we can take a look and recall that the most important thing for our equations when they're in factored form are the x-intercepts. Okay, with the x-intercepts, we first need to look, is there a bounce, is there a kiss going on, or is there a leveling off? And the answer is no to all of those. So this equation we know is going to be pretty straightforward, and we are going to, when we make our equation, put the opposites of what we see for the x-intercepts as our factor. So I'm going to leave a little space, and you'll see why here in a second. But this first x-intercept here is -3, so our factor is going to be x plus 3, because if we would solve it using ZPP, it would give us -3. And then this x-intercept right here, okay, is x plus or minus 0. It doesn't matter. So what did we do last week? We put x. And usually when 0 is an x-intercept, you're going to put that x out front. That's why I left the space. And then I have x minus 2. Okay, so now the question that was asked of us is, how can we check to see if this equation that we just wrote does also match kind of the vertical amplitude of the function? So we've done this since probably pre-algebra. The key is go ahead and pick a point, and they gave us nice accurate graphs, and we want to check if this point makes this equation true. Okay, so this is the process of checking. What is the point? The point is -2, 8. So we're going to ask with a question mark, okay, is 8 equal to, and then we have to replace every x with -2. So is 8 equal to -2 times, let's see, 1 times -4? Well, -2 times 1 times -4, 8 equals 8. So when we get a number equaling itself, we can be very satisfied that this equation does fit the graph that we are given. Okay? So that's kind of the process that we're going to go through on this first question. So you might want to pause me and try a few of these on your own. If not, keep following along. Okay, so on this next graph, let's analyze what we see. So we now see that we have opposite direction arrows, but the orientation is different. Okay, it is not like the normal cubic graph. It's like the cubic graph that is reflected over the x-axis. So we see that the opposite arrow direction means that it's going to be an odd degree. Okay, and then because we have up then down, we're going to call that negative orientation. Now from here, we want to look at where are the x-intercepts. And we see that we have -3. We see 0, but what's happening at 0? We see that the graph is leveling off, and that's very, very, very important. And then we have x equaling 2. Okay, so when we level off, if you recall from last week, the leveling off means that that x-intercept has to have an odd power attached to the factor. So when I go ahead and make my equation, okay, I'm going to actually deal with that one first, with x equals 0 first, because we said that usually goes out front. But the factor has to be raised to an odd degree. So I'm always going to try the smallest odd number, and it can't be 1. Okay, it has to be 3 or greater. And that's what we learned in 8, 1, 2, and 1, 1. And then we have x, let's see, plus 3, opposite of -3, and then we have x minus 2. Okay. So now, again, we want to check the accuracy, and if you notice, the scale on the y-axis is going up by 5s, but they did give us a lattice point of, it looks like, let's see here, ooh, I want to use this nice one. I want to use this point right here, which is 1, 4, okay? Now, it's not as clear, I guess, on the picture they gave us, so I don't really like that. But, okay, if I were to ask you to do these on your own, I would make sure that the lattice point was clear. So now we need to go ahead and check, and I'll go ahead and make a little line here to make my work clear. So we are looking at is 4 equal to... Now let's think about for a second before I get ahead of myself. We said that the orientation of this graph is negative because it's like a cubic graph that is flipped over the x-axis. So what parameter makes our graph flip over the x-axis? It's going to be a negative out front on the leading term. So I'm going to put my negative, and then I'm going to, in parentheses, okay, because we are not cubing the negative, that's very important, do 1 cubed, and then times 1 plus 3, and then times 1 minus 2. So is 4 equal 1 cubed, 1 times 1 times 1 is 1, but then I have to tack on the negative because that's not part of the cube. And then I have 4, and then 1 minus 2 is -1. So the -1 times -1 makes a positive, so what do I get? I get 4 equals 4. Check that off. So again, I can be satisfied that this equation, don't forget that negative in front of the x cubed or else it would not have worked out, okay, matches the graph that we were given. So now on this final graph, we first think about the degree. Oh, and let me backtrack for a second on graph B. Okay, what is the degree of the equation that we made? It's the 5th degree. And what is 5? It is an odd number. Okay, and then if we go to graph A, what is the degree? 1, 2, 3. The degree is 3. And that is an odd number. Okay, so maybe we add that the degree was 5. But that's easier to determine once you have your equation. So now we're going to go to this final graph, and we are going to see that again, okay, weird that they're not doing any even, but we have opposite arrows, so it's going to be odd degree. And then we see that the arrows are up then down, which is opposite of a normal cubic function, so we are going to once again call this negative orientation. So if we take a look at what's going on here, let's look at our x-intercepts, and this first x-intercept of -2 is bouncing or kissing the x-axis. So we know that when that happens, the degree on that factor has to be even. That's a special case, okay? And then we also have the x-intercept of 1, and there's nothing special about that, okay? So let's see here. My equation, I'm going to write above the graph this time. And if we think about what's going on, we're going to say y equals, and then we have x plus 2 is the factor, but we said that that needs to be taken to an even power. So we're going to start by squaring it. And then we have x minus 1. Okay, as just the plain old second x-intercept. The opposite of 1 is -1. So if we look at a lattice point, okay, and for this case, we are going to use the lattice point on the y-intercept. I'm always trying to look for nice points if you're wondering where I'm finding these. So either they give you them in bold or you find a perfect point. So I'm going to use the y-intercept that is 0, 8. And we are going to go ahead and check to see what's going on. So we're asking, is 8 equal to 0 plus 2 squared times 0 minus 1? Okay, so then we're looking at, is 8 equal, 0 plus 2 is 2, 2 squared, 2 times 2 is 4, times 1. Well, we see that 8 is not equal to 4, okay? But immediately everyone in their head probably sees that 8 and 4 are very closely related. So what do we need to do to the right-hand side of the equation in order to get this 4 to be equal to 8? What do I do to 4 to get 8? I double it. So if we go back to our original equation, we're sometimes going to have to put a coefficient out front, and that coefficient, that a value, controls the stretch factor, which we've been looking at since first semester. Okay, so if you don't have the 2 out front, it would not be the equation for the graph that we were given. So now we do care about the height of the peak and the depth of the valley. Okay, so that's called the amplitude. So we just kind of used common reasoning to say that we need to multiply, we need to multiply by 2 in order to get both sides to be equal. Okay. All right, so if we go back and look, though, what is the degree of our equation? That 2 out front does not affect it, so the degree would be 3 because you have x plus 2 repeated twice and you have x minus 1 repeated once. Add those together to get degree 3. Okay, so what is the key idea of the lesson today? 46 kind of encompasses it with the question of what is the difference between these two functions? First, we have x squared times the quantity x minus 3 times the quantity x plus 1. And then we have y equals 3x squared times the quantity x minus 3 times the quantity x plus 1. Okay, well, first of all, let's not focus on the differences. Let's focus on the similarities. The similarities are both equations have the same x-intercepts. What are the x-intercepts? The x-intercepts are 0, 3, and -1. Okay? What is the difference? It's this 3 out front. Okay, what is out front here? It's a 1, so we're not going to write it. So what is the difference between these two equations? Okay, it's the stretch factor, the amplitude, maybe you might call it. Okay, so the second graph, and I'm going to type this. Okay, so the second function is a vertical stretch of the first. Okay, so the second function is a vertical stretch of the first function. So everything is being multiplied by 3. Okay, and we can draw an arrow to show that. Whoops, what am I doing here? Let's get off of everything. Let's move this. Sorry. All I want to do is draw an arrow, and that shows your vertical stretch. Okay, so the x-intercepts are the same, but the vertical stretch is going to affect the y values, the y scale of the graph. So the last question of the first lesson of the week is basically saying, is it just enough to focus on the intercepts? And hopefully we saw by question letter C, and also by this idea right here, that no, the x-intercepts are not enough. We have to consider the stretch that is going on vertically to the graph. So if we think about the equation that a student wrote for the graph that you see on problem 47, the claim is that this function represents the graph at right. Okay, well, how do we come up with that function? We see the x-intercept of -3, so the opposite would be +3. We see the x-intercept of -1, and then we see the graph bouncing off at 2, so the factor x minus 2 is going to be squared. So, how are we going to decide if Melvin got the correct graph? Okay, well, we have to check a test point that comes from the graph. So you can't just choose a random point. Okay, we have to look at some point that is going to be accurate enough for us to test. Okay, and again, these graphs aren't the best, but I would make sure you knew what to test. But we are going to look at the y-intercept here. Okay, and the y-intercept is 0, 24. So we are going to go ahead and check and see, does 24 equal 0 plus 3 times 0 plus 1 times 0 minus 2 squared? We're asking, is that true? So then we're asking, is 24 equal to 3 times 1 times -2 squared is +4? So 24 is clearly not equal to 12. But again, this is very similar to letter C on number 45. We can quickly figure out, okay, how can I make this 12, this right-hand side we call it, be equal to 24? Well, I have to go ahead and multiply it by 2. So if I go back up to Melvin's original equation, I have to put a 2 out front. So the equation should be y equals 2 times x plus 3 times x plus 1 times x minus 2 squared. Okay, so that 2 is very, very, very important. Okay, now the x-intercepts didn't change. It's just the vertical stretch factor that changes. So how are we going to do this systematically? Because what if the numbers don't relate by a multiple of 2 or a multiple of 3? Okay, well, on B it says, before you figured it out, you could have written the polynomial for this graph as P of x stands for polynomial equals a times x plus 3 times x plus 1 times x minus 2 squared. Okay, so we did this back in first semester with parabolas when we did word problems, and the numbers got a little messy. But we need to anticipate a stretch factor, I'm going to say. Anticipate the stretch factor. So we need to hold that parameter with a place value of a. Okay, we call a parameter, not a variable, because eventually it will be a number. So what if we did not have a graphing calculator, but we were told that the graph, okay, of P of x certainly goes through 1/16. How could we use the information to decide the exact equation? Okay, well, the key idea is to plug in 1/16 and solve for A. And that'll give you your stretch factor. Okay, so hopefully this is kind of coming back to you. So I can go, well, I have 16 equals A, and then hopefully you're okay with me kind of doing the math in my head. So I'm going to plug in a 1 and do 1 plus 3. I'm right here. 1 plus 3 is 4. Okay, and then I have 1 plus 1 is 2. Write yourself a note as to what I'm doing. And then I have 1 minus 2 is negative 1. Squared is 1. So I can even show negative 1 squared. So then I have 16 equals A. 4 times 2 is 8. What's negative 1 squared? It's 1. So I have 16 equals 8A. So when we divide by 8, we get A equals 2. So what is the leading coefficient or the stretch factor of the function p of x? The stretch factor is 2. So you would have to have, you would replace A with 2. Okay, so A is not going to be in your final function. We're just trying to determine what that stretch factor is. All right. Okay, so that is day 1 of 813, exploring that value of A. So we're really paying attention to the y-axis scale along with the x-axis scale, and we are going to continue on with this concept in the next lesson. Make sure to pay attention to what homework problems I'm asking you to do, because we are splitting up the homework amongst 2 days for 813, just like we did in the previous lessons for the beginning of Chapter 8 as well. All right, talk to you later.